So good afternoon and welcome to today's colloquium. Today our guest is Bret Kugelmass. Bret is a former technology entrepreneur who has dedicated his focus to climate and energy challenges. One of the early pioneers in commercializing unmanned aerospace technology, he founded and remained the CEO of Airframe Incorporated for 5 years up until its acquisition. Prior to that, he received his master's in robotics from Stanford University, and his earlier work includes designing lunar rover control systems for NASA and a concept electric car for Panasonic. In 2017, he launched a Washington, D.C.-based research institute, the Energy Impact Center, which is focused on exploring the challenges and opportunities of nuclear power's role in deep decarbonization. Their work includes techno-economic analysis of energy technologies, hosting clean tech prize competitions, and publishing audio interviews with hundreds of experts under the Titans of Nuclear brand. So with that, let's welcome Bret to the lab.
Hey everybody, thank you so much for having me here. 2 years ago, I embarked on a very new type of journey. Fresh off the heels of your classic Silicon Valley startup story, still bright-eyed and full of ambition, I realized my former life was missing only purpose. And all that I wanted to work on was what I thought to be the greatest challenge of our time. I bet some of you in this room don't believe in climate change, or maybe know a few colleagues who don't. To that, I used to take a very adversarial viewpoint. I was combative, dismissive, so ready to call the other side idiotic. But after a while, you begin to realize that climate change, more than anything else, has become a proxy war for debating other societal values. Who deserves our help? How do we spend money? Which team am I on? Studies show that 1 billion people will be displaced in the coming decades. But is that really much different than today, where we already ignored that many who lack fresh water? Our rhetoric implies this debate is over science, black and white. But it's very easy to pick which aspects of science support your argument. And both sides, both advocates and deniers, seem to just work backwards to characterize the problem such that the only remaining solution is one that supports their worldview. A couple weeks ago, I published my first op-ed, where I spelled out the case for negative emissions technology powered by nuclear energy. And to my surprise, the fiercest opponents were other climate advocates. Now, I was the one being called idiotic. It is very easy to agree with the mantra of your tribe. But no matter how right you think you are, there is great virtue in willing to be skeptical, open-minded, consider arguments that you wouldn't normally agree with. 2 years in, and I experienced firsthand that acquisition of knowledge is a very dangerous thing. The more you learn, the more questions it may bring. So today, I'm going to tell you something you might find unbelievable. What I'm going to tell you, I might be the first person to ever articulate. And what makes this story so tricky is that those who have the greatest ability to validate my claims have the greatest motivation to do the opposite. I am here today to talk to you about nuclear power. And I will explain that a nuclear meltdown, under any circumstance that you could possibly imagine, is totally harmless. That's right. I didn't say that nuclear power is safe. This is what the nuclear industry will tell you, that a reactor core is naturally very dangerous, and only they make it safe. Their position sounds more reasonable, right? And it would be easy to argue their position to any of us engineers. After all, we are the heroes in this story. But their position has never and will never win over the general public. And their position is complete and utter nonsense. What I am saying is that a meltdown of your standard 1960s light water reactor, even without the engineers, the inspectors, the containment domes, the safety systems, the backup generators, poses zero threat to the public. And who is responsible for this debilitating misconception? Not big oil, not hippie environmentalists. Responsible for this 5-decade shackling of human prosperity is, ironically, the nuclear industry itself. Have I got your attention? Good. Now I'm going to make my case through a journey of history and physics, and then I will share with you my solution for climate change. Now, as a warning, I don't make too many friends during this talk, so if you get easily offended, here's your chance for a bathroom break. Okay. History. In the 1960s, the US started building hundreds of reactors. Not even a generation had passed since we dropped the bomb, and there was no fear of atomic energy. The world could not have been more excited to employ this wondrous power source. A fuel that had seemingly magical properties, so energy rich that a Coke can worth could power every aspect of your entire life. Physics. Not only does uranium have a 3 million times energy density of fossil fuels, it's as abundant as tin. It is 25 times more abundant in the crust of the Earth than oil and coal combined, with 75 million times the contained energy. Even better, it doesn't require mining. It's dissolved as a salt in the ocean, just like table salt. One could pull from the entire crust of the Earth from a single point in the water. If uranium were to power 100% of today's worldwide energy needs, we'd have a 25 billion year supply. I probably don't need to mention to this crowd that's longer than the Earth is going to last. History. In the 1960s and 70s, we built over 100 reactors and had plans to build over 200. The United States was set to become a fully nuclear nation. By 1990, it would have been energy independent, perhaps in time to avoid a few wars. Our predecessors talked about too cheap to meter, and while that phrase is often ridiculed today, their optimism was warranted. With that energy density and abundance? So, what happened to this promising industry? Let's take a science detour first. Physics. How does a reactor even work? Well, most people, heck, most nuclear professionals think it's a chain reaction of splitting atoms that's poised to go supercritical at any moment, but for an active control system. Not true. Via its very physics, there are 3 methods in which a nuclear reaction is held in perfect balance without any active control. The Doppler effect, the thermal expansion of water, and the negative void coefficient. A light water reactor, as its name implies, requires water to moderate or tune the neutrons. If the reaction begins to increase, experiencing a transient or a moment of supercriticality, the physics of the water across these 3 separate factors bring it back in line. A water reactor operates like a ball in the bottom of a bowl. It operates in balance, or not at all. If anything, it's tough to keep the reaction going. You see, neutrons are a fickle thing. They are electromagnetically impervious. They're designed to slip through the cracks of matter. In water reactors, a chain reaction will not continue without both water and the precise geometry of the fuel itself. If everything goes wrong and the water boils off, good. That means there's no water left to tune those neutrons and the neutrons escape. The reaction dies. If everything goes wrong and the core melts, good. This means the geometry is lost and those sneaky little neutrons escape. Not enough neutrons, no more reaction, no more neutrons. It's naturally self-diminishing. But if the reaction stops on its own, when the neutronics gets too out of whack, why does the darn thing melt down? Well, splitting the atom is not the only source of heat in a nuclear reactor. After that atom is split or transmuted, what's left has a little extra energy. Very little, in fact. Within 1 second of that chain reaction dying, the reactor is at 6.5% power. Within an hour, only 1.5%. A day, 0.4%. A week, 0.2%. This isn't very much, but it is enough to melt some metal. This is why we call it a meltdown. Now, I want to make this crystal clear. This is different from what happened at Chernobyl. Chernobyl was a graphite reactor that first exploded and then caught fire. That was not a meltdown. That is not the context of this talk. So if all that happens during an actual meltdown is that the reactor core becomes a hot, molten pool of metal, why are we all so afraid of water-based reactors? Why has virtually every nuclear engineer for the last 50 years dedicated their career to nothing else but preventing this one thing from happening? Why do we think of a meltdown as a dangerous event? History. Utilities are a weird business. Due to heavy infrastructure investment and the natural monopoly that creates, prices were strictly controlled by the government up until the 90s. They were not driven by competitive dynamics or by saving customers money. Utilities were, and many still are, compensated as a function of how much they build, own, and operate. Do you guys see the incentive structure here? Throughout the late 1960s and 1970s, in order to generate greater utility profits, nuclear power plants kept getting bigger and bigger. This is what the customer demanded: high capital expenditures. But Icarus could only get so close to the sun. Eventually, the whole industry flew into economic flames. As reactors got bigger, their supply chain became more specialized, and the construction became more complicated. As an example, both the reactor vessels and the turbines eventually became so large that they could only be transported to site by barge. There were only a couple factories in the world that could manufacture them. The cost of a pressure vessel alone escalated from $1.5 million to $150 million for a pressure vessel. By mid-1970s, every project in the country started experiencing delays. The supply chain for these specialty parts simply wasn't robust enough. 2 more factors contributed to serious delays as well. The first, however incredibly ironic now, environmental lawsuits. And the second, a brand new regulator with unlimited authority. which of course, upon inception, immediately rewrote the rules, even for projects halfway through construction. The average build time jumped from 4 to 12 years for virtually identical infrastructure. These delays extended the construction loan period, and while borrowing had never been so expensive. As a quirk of history, as all this was going on, interest rates shot up to 18% in this country. Unsurprisingly, projects ran severely over budget. The cost of the same nuclear power plant went from $400 million to $4 billion. Nuclear power, which had the promise to be the cheapest energy source ever known to mankind, had in the matter of just a few years become the most expensive infrastructure projects to ever exist. And all of this had absolutely nothing to do with splitting the atom. American utilities canceled all future orders at this point. Combustion Engineering, Babcock and Wilcox, Westinghouse, General Electric were toast. By 1978, before the words 3 Mile Island were ever known to the public, the nuclear development industry was already dead. Physics. Speaking of 3 Mile Island, let's get back to the physics of a meltdown. This theory that a meltdown is somehow dangerous to the public is predicated on the release of enough radioactive isotopes into the environment. Now, there is no doubt that a molten reactor core is very radioactive, but that's not all you need to be dangerous. To be a threat to human health, any toxin, chemical or nuclear, needs to have 3 characteristics. The first, it needs to be at a dangerous level of toxicity. Okay, that makes sense. The second, it needs to be able to move through the environment. And the third, it needs to be able to accumulate in human biology. Toxicity, movement, and accumulation. Missing one of those 3, there is no public hazard. If I were to sum up the chemicals in just the furniture of this room, it would possess a higher toxicity than anything inside a reactor. But we're not worried about these chemicals. How the heck would it get inside of us? Why, when it becomes waste, do we just toss it in a landfill? Because even normal landfills are designed to very inexpensively control the movement of waste pretty easily by just tossing some dirt on top of it. And if little bits do move over the years, that's fine. By definition, that prevents the accumulation piece because it takes a very long time. Quantity, rate, distance. These factors matter when defining a toxin's risk. When a reactor melts down, it releases over 100 different isotopes. Some with a lot of energy, but that lasts just mere moments. Some with a tiny bit of energy, but that lasts millions of years. But there are only 3 such isotopes that are in the Goldilocks zone of toxicity and movability. The real word is volatility, but for purposes of clarity, I'll use movability. Those 3 are cesium-137, strontium-90, and iodine-131. And of those 3, there's only one that can actually accumulate. Iodine-131. Now, what's so amazing about iodine-131 is that it just has an 8-day half-life, which means it's entirely gone within a couple of months. Not millions of years. The dangerous part is gone within 2 months. History. I told you those nuclear developers were toast, right? No, that's not exactly true. Westinghouse's business had two sides. One side developed power plants. The other side sold services into utilities, equipment upgrades, safety modifications. Now, let's take a minute to think back to the Great Recession, right? 2008. What if we just let the auto industry collapse? If we didn't bail them out? If all the car developers went out of business? Think about the two sides of the auto industry. What would happen? The auto repair shops that were still around with no industry pushback would have lobbied for regulations that grew their business. And before you knew it, you'd be pulling in for a full inspection every 100 hours of driving. After all, better safe than sorry. Back to reality. 1979, 3 Mile Island. An expensive piece of equipment broke in an empty room. Now, of course, there was media attention, playing off the recent China Syndrome movie. They sent reporters in for the hot scoop. But by now, remember, there was no nuclear developer industry left. There was no communications team they sent out to ridicule these reporters, no lawyers to sue them for effectively yelling fire in a crowded theater. No, the developers were long gone. What remained was the services industry. And the services industry did the opposite. They fed the fear. After all, their business was selling safety upgrades. Now imagine you're Jimmy Carter. As the hysteria grows, you call in the experts from both sides, the nuclear industry and those critical of the nuclear industry. And both sides are now telling you the exact same thing, that a meltdown is a catastrophe that must be avoided at any cost. Do we see where this all goes? Where for the next 50 years, both the nuclear services providers and the non-nuclear energy providers benefit from a public fearful of radiation. Regulators would respond to public concern by decreasing the tolerable thresholds of exposure by orders of magnitude. And after 50 years of brainwashing, it has become common understanding that a meltdown is the definition of catastrophe. Physics. Just to give you a sense of how crazy this has gotten worldwide, in Japan, you are only allowed 0.04 becquerels per centimeter cubed of iodine-131. Now, a becquerel is the disintegration of a single atom. The regulatory bodies imply a dangerous dose is 1/25th of an atom. The regulations for iodine-131, when levelized across rate and volume of exposure, are 5 billion times more strict than arsenic. Now, please allow me a moment to mention that vending machines, escalators, champagne bottles, and hot dogs each kill a dozen people a year. Iodine-131 maybe has killed a dozen people in all of human history, and it definitively saves millions every single year in medical procedures. Iodine-131, the isotope that we theorize induces thyroid cancer, is used to treat, anyone? Thyroid cancer. History. After the radiation standards were escalated, the industry got exactly what it wanted. New regulations followed, mandating an extra $300 million in safety upgrades for every single one of the existing plants to prevent in reality what was an equipment malfunction in an empty room. Riding on the success of 3 Mile Island upgrades, nuclear services had cemented a new business model. Take every opportunity to scare the public, leverage the all-powerful regulator to sell ever more safety systems into existing assets, mandate capital expenditures on the rates of the taxpayer. 1986, Chernobyl. This plant was a graphite reactor designed specifically to make plutonium. It is as different from a water-based reactor as a fireworks factory is from a furniture factory. But by this time, 0 companies were incentivized to explain this difference. Westinghouse sold another $400 million in safety upgrades for every commercial nuclear plant in the US, even though none of them were based on graphite. 1989, Hanford closes down, and since then, over $100 billion has been spent over 30 years digging and refilling holes in the middle of the desert, even though there was no iodine-131 left after 2 months. 2001, September 11th. This time, security upgrades. 115 armed guards per plant, aircraft shields, missile shields, money, money, money. 2011, Fukushima, an earthquake, a tsunami, blackout, fires, 20,000 drowned, and not a single person was affected by radiation in any way. And despite this, the Japanese government will spend $200 billion on cleanup costs. This was the new nuclear industry's biggest payday yet. Physics. At Fukushima, when a tsunami flooded the reactor building, it took out every single safety system. Can anyone wager a guess as to how much iodine-131 escaped? In the absolute worst case scenario, from 3 gigawatts worth of core meltdowns, 28 grams. 1 teaspoon. This is what the nuclear industry calls a catastrophe. This is what society believes is a catastrophe. 1 teaspoon of toxin being released. Every nuclear conference I go to, I offer $10,000 to the first person who can show me any plausible scenario where even a single member of the public could get hurt from a meltdown of a light water reactor. I've offered this to thousands of industry professionals, and that challenge still stands today. The result of the US nuclear industry perpetuating the myth that a nuclear meltdown is a disproportionate hazard is that we take disproportionate measures, and in doing so, we actually make it one. At Fukushima, where 0 people were ever at risk of radiation, the government killed 1,000 of their own in botched hospital evacuations. Then, they forced 100,000 more to abandon their homes for years, as they paid the nuclear services industry to clean their land. All because a teaspoon of radioactive iodine-131 was released. But this is the nuclear business model post-1970s. They do not sell electricity. What they sell is protection. What they sell is fear. Okay, so what does this all have to do with climate change? I'll get there. But first, let's remember, it is the magnitude of carbon dioxide that's in the air that controls the rate of heat addition. Since we're at 410 parts per million after having added 1 trillion tons of CO2, this corresponds to a radiative forcing, a net addition of heat of 3 watts per square meter. Okay? Now, every single manufactured item has a carbon footprint, including clean power. In manufacturing, we use materials, chemicals, and energy that at some point had to be derived from fossil fuels. On top of that, with some renewables such as solar, you literally have to burn coal to turn the silicon dioxide into the requisite purified silicon, and its direct product is carbon dioxide. All clean power increases the magnitude of carbon in the air. All clean power increases the rate of heat addition. If we were able to cease all emissions tomorrow, the Earth would not restore to pre-industrial magnitude of carbon for tens of thousands of years. It just doesn't sequester carbon that quickly. In the last 100 years, we've burned 100 million years worth of naturally sequestered carbon. The only possible solution is negative emissions technology, direct air capture of CO2. Anyone on team science who ignores this clearly isn't on team math. And now, if the implication of this wasn't challenging enough, it gets worse. Since negative emissions technology will require energy, and all energy has a carbon footprint, being low carbon isn't good enough. The energy source that you employ has to be so ridiculously low carbon that it can not only extract 1 trillion tons of CO2 from the air, but also account for its own compounding carbon debt while doing so. Now, this brings us to nuclear. Remember that Coke can that we started off with? Well, considering that any system's carbon footprint is a function of material consumption, nuclear, being orders of magnitude more energy dense than any other option, is the only energy source whose footprint is below the carbon threshold required to power the capture of carbon in a negative manner. Nuclear power is not part of the solution. If you care about math, nuclear is the solution. But let's also be realistic. We need about twice as much energy as is globally produced today to pull that much carbon from the air. Who's going to pay for that? And should we even bother? Why is climate change bad? Warm here, cold there, who cares? It would be great to care quite as deeply for nature, but at the end of the day, I'm on team human. And we have 2 billion teammates who are going to suffer from any sudden changes to precipitation. That's why it's bad. 2 billion people who simply do not have the tools, capital, or know-how to adapt agricultural practices fast enough. For God's sakes, they're not even planting crops in rows yet. So we have to ask, do we spend tens of trillions of dollars tackling emissions and maybe not even solve the problem in time? While all that money could have gone to growing the economy and making the poor less vulnerable? Is it possible that in trying to solve climate change, we could actually make the practical consequences worse? I don't have the answer, but this is the conversation that we need to have. We need to have a clear-eyed assessment of how bad things will be if we don't do anything, but acknowledge how bad things could be relatively if we don't do the right things. Or, there's a third approach worth considering. Why don't we try a little bit of convex optimization? Let's set the bounding conditions of our problem as a win-win and see if there's a solution that emerges. Bounding condition 1, energy needs to be cheaper than ever. Bounding condition number 2, we don't tax the economy or force anyone to change their lifestyle. Bounding condition number 3, we do all of this while removing carbon from the air. Any solutions come to mind? It took me almost 2 years to derive one. We must make carbon-negative fuels that are cheaper than carbon-positive fuels. It is the perfect alignment of short-term individual interests and long-term global preservation. The faster we consume, the faster we solve the problem. How do we do this? Well, if we can produce nuclear heat 3 times cheaper than fossil fuel heat, we can cost-effectively pull carbon from the air, recombine it into synthetic fuels, some of which get burned in a net neutral manner, but then some of which get permanently sequestered as the products that those fuels go into and the building materials. And the system is on net carbon negative. Cheaper than ever before, incredibly inefficient from a heat perspective, but who cares? It can be applied globally, instantly, without forcing changes to infrastructure or way of life. And the only thing that we have to do to make nuclear that cheap is undo the regulatory shackles that the industry self-imposed 50 years ago. A 1968 nuclear light water reactor is still, to this day, the cheapest, cleanest energy mankind ever created. Yes, what I am telling you is that we don't need any new technology to unlock a future of global health and limitless prosperity. All we need is a new mindset. As I said before, the acquisition of knowledge is a very dangerous thing. The more you learn, the more questions it will bring. But if we embrace the challenge and persist through, there is nothing beyond our grasp. There is nothing we can't do. Thank you. Wanted to leave plenty of time for questions, so.
Sure. Any questions for Brett?
Please, in front.
Yes, I guess it's interesting how nuclear energy and nuclear stuff because nuclear is relatively small and it seems like it would be good for that to propose your kind of idea and take that of the market. I don't know, be ahead of the market and something like
There is no nuclear development industry. And when you think of the nuclear industry, you think there are companies out there that sell power plants. Those just do not exist. But there are companies that sell radiation protection. It's just
what are the current
they're run by the utilities. They were commissioned and sold to the utilities in the 1970s. But they're the companies that would be in the market to sell a product, like Westinghouse and GE once were, like Combustion Engineering, Babcock and Wilcox, Siemens, many of these businesses, they shut down the part of the business that sold nuclear power plants. And the entire business that exists today sells nuclear services, which is mostly selling radiation protection, equipment, services, strategies, data analysis into the utilities which own the existing assets. But there's no one left that actually sells nuclear power plants.
The next question would be, you said price. If I want to make a gigawatt hour of fuel, fossil fuel, or with one of these light water reactors, which one wins?
If you think about, there's a very easy way to think about it. Oh, sorry. Which one wins if you were to make power from fossil fuels or from nuclear power? Now, a thermal power plant, whether it is burning coal or whether it's extracting the heat from the fuel rods of uranium, is virtually identical infrastructure, okay? But 75% of your cost of electricity from a coal plant comes from the coal itself, whereas a negligible percentage comes from the uranium in a fuel. So you can estimate the cost of a nuclear power to be 1/4 that of coal if all regulations were the same, just from a strictly infrastructure perspective. That means they'd be producing power at $10 a megawatt hour. Coal produces on average across the world $40 a megawatt hour, and it's still the cheapest energy source that most places can access. Southeast Asia is building, or Asia as a whole is in the process of building 1,600 new coal power plants. Today, even with all the, everything that we hear about renewables dropping down in cost, 1,600 new coal power plants are being built because it's the cheapest energy source. Nuclear could be 1/4 that price if all we built was that 1968 plant over and over and over again. Please.
What about the issue of the so-called spent fuel from light water reactors?
Yeah, the question was about what about the spent fuel? Spent fuel wasn't something that was considered dangerous up until this shift in the industry's behavior changed. It was considered a waste stream just like anything else, didn't have that much regulations around it. The federal government took care of it. They just diluted it like we do other industrial toxins. You just dilute it and it becomes not a problem. And then when the shift came and it began all about selling radiation protection, that's when it was mandated that you have to store it for 1 million years. Why? Because the cost to store something for 1 million years is astronomical. And so, as we mentioned before, the only dangerous toxin that comes out of a nuclear reactor because of its ability to accumulate in biopathways is iodine-131. I can guarantee you there's no iodine-131 in any spent fuel that's over 2 months old. Please.
To slacken the regulations on reactors now and to start diluting the spent fuel again, and not storing it anymore?
The question is, should we loosen the regulations? Yes, we should reset them to exactly what they were in the 1960s. 1960s. If we reset the regulations to the 1960s, you'd have the cheapest, cleanest energy source everywhere in the world. Prosperity would increase. There'd be unlimited clean water, and everyone would have clean air. And all we have to do is build exactly what we built back then and set the regulations for that. By the way, those plants, there's 26 of them from the 1960s that are still running today. One of the arguments I like to take to the regulators is, okay, if that's not safe enough, shut them down. If you really think they're not safe enough, shut them down tomorrow. And if they are safe enough, let us build more of them. Please, in the back.
Do you see a role for nuclear power in hydrogen extraction? Would that create a negative fuel source?
Yes. The question was, do you see a role of nuclear power in hydrogen production? 100%. I think that is one of the greatest future use cases. Hydrogen is an amazing medium to transport chemical energy. I think it's going to be the future of powering planes and ships and cars. Its byproduct is water. How much better does it get? Half of the energy equation is sitting in the air, and its waste stream is water. Hydrogen is amazing. And you can create hydrogen from water using high-temperature electrolysis produced by nuclear energy. Please.
So to follow up to that question, by the way, I'm the one who emailed you yesterday. I'm not sure if I could make it. You've answered some of my questions, but you've addressed CO2. You haven't addressed CH3, which can be considered in some circles more of an issue than CO2. So does this technology purport to remove CH3 as well?
It's a good question. There are other greenhouse gases. So what do we do about them? Well, CO2 is the one that we often treat as the bad one because it persists in the atmosphere for thousands of years. So even if you were to stop production of it tomorrow, it would still have a warming effect for thousands of years. That's why it's such a big issue. Some of these others, like CH4, methane, they have I don't know what the exact term is, but in atmosphere lifetime of, let's say, on average 20 years. So if you stopped the emission of them, it would subside over that period of time. Now, of course, what I'm actually advocating for is direct air capture. So if you could produce technology that's already pulling giant quantities of air and separating out its constituent parts, you're pulling out the CO2, perhaps you could reconfigure it to also pull out some of these other greenhouse gases. And maybe some other things we don't like too, right? If we're building these giant atmospheric air filters, let's pull out some of the lead, let's pull out some of the cadmium, let's pull out some of the arsenic. Now you guys probably don't realize this, but you are breathing in heavy metals that are in the air every single day. So this could be the Brita for the atmosphere is what I'm proposing. Please.
So say you do manage to change the regulations. What's to say that, you also said that part of the downfall of the nuclear development industry was brittle supply chains and overly specialized complex parts. So what's to say that those same economic forces wouldn't rearise?
Great question. The question was if what tanked the nuclear industry to begin with was custom supply chains and economic and how markets were designed, what's to say that wouldn't happen again? One thing happened in the 1990s in the US at least, which was, it's termed deregulation, but it's really setting up wholesale and retail markets in the electricity sector, where the retail markets can be competitive, where you can actually have one power plant competing against another power plant. Those forces didn't exist in the 1960s and 70s when they started escalating in size. What I imagine will happen if the market is set up correctly to value cheap energy, which I think that's what we all want, right? The natural result of that would be smaller nuclear power plants that comply with existing supply chain. So the high end of your nuclear power plant would be based on whether you could procure a pressure vessel for $1 million instead of $150 million. And that's how the power plants would be right-sized.
What's the minimum size? A house, parcels, or maybe an island?
The question is, how small can one of these nuclear power plants be? Well, I mean, it's pretty amazing. NASA's working on one that's, I think, like a megawatt sized for space exploration. You know, if you're gonna put a base on Mars or the moon, it's going to be a nuclear power plant. I can pretty much guarantee it. And so you can make them a megawatt scale. You can make, there's one in Oak Ridge right now that is the size of that podium and produces 80 megawatts thermal energy. Can you guys imagine? I mean, think of a wind turbine that produces 2 megawatts electric, and how big it is, how much material it is, how much construction went into it, setting it up, the crews, the roads, the fields that you need to encounter. And now imagine something that this size, sitting in a pool of water, can produce 80 megawatts? I think we're going to see a lot of those. I think that's probably the right size. Please, in the front.
What role do you see later generation reactors, say, pebble beds and molten salt that came into existence after this plant?
Yeah. Question, what role do you see for other types of nuclear technologies, such as pebble bed, which is a graphite reactor? There's also molten salts out there. There's reactors that are based on lead, so the neutrons aren't moderated as much. What's interesting is in the 50s at Idaho National Labs, they built about 53, I think is the number, of these different type of reactors. And throughout the 60s, when there's more of a marketplace for innovation in the nuclear sector, I think there were something like 24 private companies. General Atomics got in the game, Siemens, that were experimenting with all these different types of reactors. There has been a lot of hype as to different nuclear technologies because of scientists not fully understanding what hurt the nuclear industry to begin with. And so they're hoping for a miracle. They think one of these new technologies, if we just built it, if we just designed it, people would think that it's safe, and therefore we could scale these up. But that is not what has hurt the nuclear industry. What has hurt the nuclear industry are these self-imposed regulations. Water is an incredible medium to transfer heat. Incredible. Doesn't have the highest heat capacity, right? But it has the highest volumetric heat capacity, okay? Which means that your ability to move heat from point A to point B is the best with water of any other material. Water is amazing. This is why coal plants, which haven't been shackled by these regulations, still use water to move heat around. So, I think that there's probably other niche applications for some of these different reactor types, but for power production or for heat production, water, 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 water is the best. What else we got?
What's keeping countries like Russia and China from adopting their own regulations, including nuclear power plants? It's not happening.
The question was, what's stopping China and Russia or other countries from doing this? I'll answer that question in two different ways. One, they are adopting their own regulations, and they've already done certain, like China has already gotten rid of the security regulations. So their nuclear power is essentially a copied American reactor, but without those 115 security guards, and so their operational costs already are lower. I imagine that trend will continue, and after they hear enough of my talks, I think they'll get rid of safety features altogether. And it won't be a bad thing, because remember, the meltdown of a light water reactor is not a hazard to public health. But the industry is a very tight-knit community. It suffered from groupthink, and so at the end of the day, everyone just builds the same things that the Americans built. A Chinese light water reactor is a virtual carbon copy of an American light water reactor. I don't know if they just don't have a mature enough industry yet to make their own like high-level design decisions. But even for them, it cost them $5 billion to build this thing, and for a $5 billion project, maybe you guys know this, how the decisions get made isn't always what, one of the engineers in the middle might think is the best decision. Sometimes other forces dictate what the project looks like at the end of the day. Please, in the back.
And so what type of reactor is Bill Gates trying to build in China?
Yes. What type of reactor is Bill Gates trying to build in China? Well, Bill Gates isn't building any reactors. Bill Gates invested in a company through his CTO of Microsoft, Nathan Myhrvold, to build what was first called a traveling wave reactor, and they now dropped that and is now a molten salt reactor. He is championed as like a way to get that company great press attention and to bring a different outsider voice into the nuclear industry. But Bill Gates pretty much has nothing to do with that project on a day-to-day basis. I think once ironically, he went to Congress asking for money for it. Listen, I think Bill Gates is a great guy, but I don't think he knows much about nuclear, and I don't think he cares enough to really push that effort as far as it needs to go. But to answer your question about the technology, it was first they were calling it the traveling wave reactor, which was a hypothetical reactor concept that didn't pan out. And then it became a molten salt reactor, which not as good as water. Doesn't have as robust a supply chain. It's got all sorts of other problems like, remember when I talked about that negative void coefficient, one of those three forces that bring the reactor back in line if anything gets too out of whack? Well, a salt reactor has a positive void coefficient. And so it can spiral out of control as things get hotter and hotter. So I don't know what he's up to. Please.
Yes, it seems that most of the carbon capture techniques that we've tried in this country has fallen apart because of various technical and economic problems. What's to keep the carbon capture part of your scheme from having escalating problems just like the nuclear industry?
Yes. Carbon capture has had problems so far. What's to keep that from happening again? There's two different types of carbon capture. One type of carbon capture is the capture that you'll essentially hook on to an existing fossil facility where the concentration of CO2 is much higher. I think what's kept that one from progressing so far is the fact that it really hurts the economics of the coal power plant, and so there hasn't, the industry isn't really excited about that. Imagine if on the exhaust pipe of your car you were to shove some rags in it. Think of how the performance of your engine would change. That's what these capture systems are for that. The technologies that I'm most excited about are direct air capture, right? Because you don't have to even negotiate with a coal plant. You can just put them anywhere and start filtering the air from anywhere. These have been demonstrated in the commercial sector with companies like Carbon Engineering and Global Thermostat, and they've been demonstrated and actually were pioneered by your guys' biggest benefactor, the Navy. So the Navy tested this technology a long time ago to produce jet fuel on their ships. And so I'm actually imagining the exact scenario that has already been developed. A nuclear-powered power plant using direct air capture to create fuel. And was already done by the Navy, just commercially scaled up. Please.
What made you decide to investigate this in the first place and question that nuclear power is dangerous?
Yeah. What created my personal investigation of the space and began to question the idea that nuclear power is dangerous? So when I started the Energy Impact Center, the goal was just climate change. We ran the math and realized how important nuclear was. And just, I don't know, maybe it's because I'm a mechanical engineer. Something really bothered me about the fact that it had this 3 million times advantage and was twice as expensive as coal. Like I just knew something was wrong. And everyone that I asked kept giving me these bogus answers. Oh, public perception. I'm like, okay. There's plenty of other industries that suffer from negative public perception and can still thrive. The chemical industry, the textile industry, the weapons industry, right? It is possible to deal with negative public perception and still be a growing business. So I just couldn't let it go. I ended up, before I developed this thesis, I completed 865 interviews in the first year of running the center across policy, industry, economics, regulatory, technology experts. And it really took 865 to realize that the nuclear industry was its own worst enemy. I know some people are leaving now. Are we wrapping up on time, or do we still have time for a few more questions? Okay, great. Yeah, please.
What would you say are the next steps to take to kind of push the nuclear industry in the right direction?
What would you say are the next steps to push the nuclear industry in the right direction? Well, my organization has spent all this time doing research, coming up with these economic models, trying to put this educational material out into the world. Everything that I'm saying, if you want backup, if you want to hear it through the interviews of the nuclear experts themselves, go to titansofnuclear.com, where I posted all of these hundreds and hundreds of interviews up online. And so we've been in the research and education mode so far, and now it's time to get into impact mode. And so we're building up another part of our organization, which is something like an international lobbying arm. And we're going country by country, meeting with regulators, laying out the math to them and showing them how much air pollution is hurting their country and how little radiation would. That's our next steps. I also hope that many other organizations take this information and run their own way with it, so we can create this reality where nuclear power is cheap again. You had a question? Yeah.
Have you thought about trying to kind of rebrand the way you present this argument? Because I feel like it's going to be really hard to beat public perception. It's not like they're going to try and understand with low-level physics.
Yes. Yeah. So the question was, have I tried different ways of branding this argument? Yes. So I have about 10 different presentations. This is the one for an engineering audience. I figured the folks at APL would like me getting into some of the math, and so that's why I did that little history, physics type thing for you guys. Our main theory is that you can't change public perception directly. I mean, these companies spend hundreds of billions of dollars in marketing their own solutions and the value of their own solutions. Our thesis is that only economics can eventually shift public perception over time, and so our goal is to find a safe space for nuclear development somewhere in the world, show that it can be built extremely cost effectively, have that become a domino effect for one country after another that wants clean air, clean water, and abundant power. And then eventually it'll come all the way back to the US. Some rule changes will be made, and maybe 20, 30 years from now, when people have field trips to the local nuclear power plant, they'll begin to love it again. Please.
Given the perception of nuclear, could you speak to France and how the majority of their nuclear, or the majority of their energy production is nuclear?
Yeah.
So do they just buy into your thesis?
Yes. The question was, given the public perception challenges in nuclear, what did France do that they were able to produce 80% of their power from nuclear energy? France is a small country that got hit hard in the oil embargo crisis, and just made and by the way, France also has a bunch of really talented engineers that come out of their education program. And so they made a very swift decision to just build a fleet of nuclear reactors for energy security purposes. They built the exact same one, essentially, over and over and over again throughout the country. It was extremely cost effective. France probably has the cheapest energy of any country on planet Earth. And it's just been a huge, huge success. Now, I'll tell you what has changed that's a little bit sad. They used to do those school bus tours to the local nuclear power plant, and they stopped that about 20 years ago. And polling shows when they stopped sending the school children to the nuclear power plant, that the public perception has started getting worse and worse for nuclear power. So it's an active effort. If you want to promote your industry, your technology, it requires continuous work, continuous education, continuous marketing that never ends, and you can never let up. So that's a good lesson learned for the rest of the world.
One more question.
I understand where you're coming from here, basically wrapping up kind of the nuclear development industry. Do you see in this future of nuclear heavy energy production any space for other or renewable sources of energy as well, or kind of just like building up energy resilience, or what do you see as do you see any sort of other puzzle pieces fitting in there?
Yeah. The question was, what do you see for other energy technology sources in this future? I mean, I think from the mathematics of it alone, it's going to be just overwhelmingly nuclear. Of course, there will be niche applications where solar panels make more sense. Maybe niche applications where wind makes more sense. But the three main components to the system that I imagine is going to be direct air capture technology, nuclear, and then synthetic or hydrogen fuel creation. Those are going to be the three key technologies that enable rapid dissemination of every type of energy source that we'll ever need.
I'm sure Bret would be happy to hang around and answer more questions. Let's thank him.
Thank you, guys.